So, Assalamualaikum warahmatullahi wabarakatuh. Um, we're back again. So this is the our fifth meeting, right? So we've discussed about a little bit about the refinery and a little bit about optimization, and these two courses you should have them studied or learned before taking this course, right? And then this course is more like merging these two topics together. And then the third day we discussed, the third meeting we discussed on the project and then hydrocracking unit, and then how we can do something with that. And then the fourth meeting last week was more on hydrogen network or hydrogen pinch or hydrogen management. So, where it draws the similarity with heat integration, and we also use mathematical programming, and then in the class we use the linear programming to show you how to solve the hydrogen network in a simple manner. So today I'm going to share. Yeah. So today we will talk about what we call real-time optimization, or well, it's refinery-wide optimization. Yeah, refinery-wide optimization. But the example that we are going to discuss, it's not about refinery example, but then the concept is the same because I don't have any refinery example with me. But nonetheless, so these are the books. As always, I give you the um, the relevant references for each of the meeting, and then in this case you can read this in addition to this 1 2 3, you can read this number 4, number 5, yeah, especially number 5, and then you can read number 4 and then number 6. Okay, so these are the main references that I'm now using for the current slides. So we will discuss on yeah, before we go on the refinery wide optimization, or so we need to talk about three things now. We need to talk about the process modeling and optimization, and then real time, what people say as real time optimization, and then an example on refinery wide optimization. Yeah, so I hope we can cover them all. Otherwise, yeah, we have to cover them all nonetheless. As always, if you have any question, just ask me. Okay. If you think that I am too quick, well, I cannot slow down because we have only like 2 hours to cover. So please bear with me. So process modeling optimization. So we have touched this very frequently already. Now, before we go on the RTO, there is a concept that I would like to share with you. So the concept of mode of calculation. So I think some of you are aware already, some maybe not, maybe all of you are aware already, but nonetheless, just to set some basic here. So there's a concept called a sequential modular and an equation oriented. So in order to solve a flow sheet, like if we have a flow sheet like this, so we have a feed coming in, and then we have a recycle, and then this recycle is then mixed with the feed and then sent to a reactor where a reaction happens, and then the product and then the unreacted feed, they are recycled back to the reactor, and then the product we have on the bottom. And then we may have some impurities either from the gas makeup or in the feed, whichever they're coming from, and then that unwanted or impurities, maybe they are inerts or maybe they are produced in the reactor. Nonetheless, if they are accumulated here, we have to get rid of them. Yeah, remember in all. Yeah.
So what is again SMTO?
SM is sequential modular. SM is sequential modular, and then EO is equation oriented.
Equation oriented. Thank you.
Yeah. So Yeah, I mean, it's always in the plant or in real life or in also in calculation. So we have to, for each of the components that we have in the system, for each of the components that we have in the system, it has to have a way to get in, like for example from the feed, and it has to have also a way to get out, either via product or via the purge. Yeah. So what's coming in should be equal to what's coming out. So that's basically the this thing. So how does it work basically? How does it work? What is then the difference between this and that? So sequential modular is basically the way that if you know software like Aspen Plus, so it works like a sequential modular. So it has this fit. So we define the fit. Yeah, we define it, and then we go to this mixer, and then in this mixer, before this stream can be calculated, this mixer it has to have information on the recycle stream. But as we know, when we first model this, there is no information on the recycle stream. So in this case, we have to make a guess. We have to make a guess. Yeah. So we define our feed, and then we define or assume something here. Yeah, we assume something here, and then if we know this and then we know that, and then this thing can be calculated. Okay, and it goes here in this exchanger, and then if we put in the information related to the performance of the exchanger, for example the pressure drop, and then the required duty or the outlet temperature or delta T, and then this guy, if we input here information, and then this guy will be calculated. Okay, so we know this, again we know this, we assume this, and then this is going to be calculated, and then so now we know, and then we input information on the block, and then this thing, this stream, outlet stream, will be calculated. So it will then calculate block by block, and then also by block by block, like this. Yeah, so we have the input information calculated, we input the performance of the reactor, this outlet stream will be calculated. Okay, and so on and so forth until it reaches this flash or distillation or separation unit, whatever. So we input the performance of the separation unit, and then it will then calculate for us this stream and then that stream. So this stream, it also goes to this purge, and then we also input the performance of the purge, either 50% or 20% or 30% or whatnot, up to you. So once we know the split factor, so this stream will be split into this stream and that stream, and then it goes to this compressor, and so on and so forth until it goes to this mixer, and then we have like a gas makeup or something, I don't know, the stream makeup, and then after here it will be calculated from here, both this information and that information. So now at this point, for example, we have information of this stream, which is calculated information, and then previously we have another set of information also from this stream, right? But that one is assumed. Yeah, so this is assumed at the beginning, and this is then calculated. So now this stream is what we typically say as a tear stream, so we tear it apart. Yeah, so because we have an assumed information on the stream, and we have a calculated information on the same stream, so the goal is that how to make sure that the calculated number over here is the same as what we have assumed before. So okay, so again, the sequential modular is then working by block by block. It will then calculate it. That's why we call it like a sequential modular. So if we see this as a module, this is a module, that's a module, this is another module, that's another module, another module. So it calculates everything in sequence up until it gets to the first, I mean to the point of the beginning. So it over here, and then we have to reconcile the difference between the calculated value and then the assumed value. And there are several methods to reconcile this. And then I will show you. I mean, well, I'm not going to show you, but then I will tell you. There's like a direct substitution, so we can just simply say, okay, so this is the calculated one, so I will use this number in this here. Yeah, in here. So then you will then have to repeat the calculation again. So if we have a fixed a feed, and then we have a calculated value over here, and then you calculate this, calculate that, calculate this, calculate that, calculate that, calculate that, calculate that, calculate here, and then you will then compare the new calculated value with the previous calculated value. Are they the same or not? If not, then we have to then repeat the sequence again. That's one approach. Or there's also some successive substitution or Wettstein method or Newton's method or what else. So there are a number of solver to do so. So that's basically how the sequential modular try to solve recycle streams. So imagine that you have many recycle streams like this, I don't know, and then like this. That will then create lots of problems in the sequential modular type of calculations. And then in real life, so in the plant, most often than not, we will encounter many recycle streams, which may be important, which we have to include, and maybe not important, which we can omit to simplify the problem, right? So in some cases, we can solve it using the same sequential modular approach like this one. But in many other cases, we cannot solve it because of these recycles, and it will take us like a long time to solve it, or we will not be able to solve it at all. And so another approach is what they call equation oriented. So instead of calculating this block by block, and then each block we already have like the performance evaluation equations, right? Because each block we have the equations. Like for example, in this heat exchanger, we have MCP delta T, we have UA delta T LMTD. This reactor we have kinetics, and then we have also pressure drop if it's a fixed bed. A flash as well, we have like a flash calculation and so on and so forth. So instead of solving this by module like SM does, so it will then take out the whole equation, and then it will then simply calculate the whole mass balance, make them in all equations, and then they will then minimize the error between them. So in this case, if you can see, if you put all of these equations, you will then see the errors. In this very simple example, the only error here is this error, right? This is then the only error. So it will then try to minimize this error in such a way that it will then converge the whole flow sheet at once. Okay, so they use also the same kind of optimization solver like Newton, the SQP, and Boyden and whatnot. Yeah, so it's just a matter of how they approach this. The solver can be the same, but then how they approach this is the calculation is doing this sequentially block by block, or they take all the equation at once and then solve them simultaneously. So I have this I have an example. So I have an example. I don't know if you can you see this? Hope you can. So we have, for example, this is a stupid example that I made. Yeah. So we have, for example, I don't know. So to make things very simple, it's all something which has the same molecular mass, and then these are like if you want to call it, if it's the same molecular mass, that means it's either mole flow rate or mass flow rate. It doesn't really matter. So we have like A and D. A and D being like a light components, and then B is like a heavier components, and then they mix it, and then here we have another stream coming in, which is the like a recycle stream, like the example that I mentioned. So we have all of these streams mixed together, and then they go to reactor, and then they go to separator, and then the product is then the reaction is then A plus B becomes 2C, and then the product is then C. C is then the product, yeah. And then the unreacted A and B will then be separated. So B is then it doesn't go up. So here we have the separation factor to the top. So 100% of A goes to the top, and then 99% of B goes to the top, and then while B nothing goes to the top, and C also nothing goes to the top. So in the top we have only like A and D, and a bunch like a 20% goes here, and then the remaining 80% goes here, and then here is then the calculated value. This is then the assumed value. So at this initial point, we have A equals to 8, D is 1, B is 9, and then the recycle, since we don't know, we simply assume 0, 0, 0, 0, 0. So we have all 0, and then you can see A is then 8 plus 0 becomes 8, and then D is then 1 plus 0 becomes 1, B is 9 plus 0, 9, and then C is also 0. So that's basically what this is. And we have like a performance of the reactor. So to make it simple, like 80%, right? So 80% means yeah, 80% of this will be reacted, 80% of B, and then this is to A. So 80% of A, which is 6.4, will be converted and will also consume the same amount of B, and then it will then produce twice the amount of C. And then we'll do the mass balance, and then here it's just a split factor also for the separator, and then the purge. So this is the initial flow sheet, how we calculate this. So sequential modular, it works like this. So we have this, and then we have that, and then we have here, and we have that one, and we have over here, and we split them. We calculate here, we calculate to the top, and then from the top we specify the purge, and it will then calculate the purge, calculate the recycle stream, and that recycle stream here is not the same as the one that we assumed before, right? So so we have this error. So I put an error over here, and then this is the total error. Okay. So that sequential model, how does it do that? It will then see the error between them, and then it will then just simply substitute. And I have like this successive substitution. So we can go to the book of like a tolerance not Turton. So they will then explain to you what this successive substitution is. So it's like a lower version or easier version of Wexline, but it's more advanced. I mean, slightly advanced than simply direct substitution. Nonetheless, so if I click this, so if I get this, it will do something, and then it will then update this to 0.64, 0.4, and so on and so forth, and it will then make the same calculations up until here. So the calculated value will become a new number, right? You can see the error. It was I forgot to say. So the error was 2.26, and then if we do the substitution, it's very slow because I'm running another simulation. So the error drops from 2 to 1, right? So we are now, and then we do another calculation. So from 1 to half. So now you see it's now it's getting converged, and then the third trial. So 2.4, the fourth trial, 2.2, the fifth, 2.2, and then the sixth, and so on and so forth. Yeah, you can see how the error is becoming smaller and smaller. So until a certain criteria, for example, in this case, well, if I want to do like I'll do 2 more. So if it's like lower than 1, if it's lower than 0.1, I assume I consider that as a converged situation. So I'll do another one. And then so this is already lower than 0.1, so that's my cut point. So lower than 0.1 the error, so I can see this is then the same value, this is also the same value. I consider them as the same value basically. So in this case we are converged. Yeah, so that's how the sequential modular works in a nutshell. And then how about the equation oriented? So the equation oriented is basically the same. I mean the same flow sheet, but it's just like it takes into account the whole calculation. The text. I mean it's not visible here, but the idea is that we try to minimize this as much as possible, not doing the calculations over and over again, but in one shot we try to minimize this. So what I did is more like so I will remove this. And then I go to the solver like we do already quite some time. So we want to minimize this total error by changing this assumed value, right? Because then this is then the x variables, and then we say that I put a constraint over here because these two, this is like this part is then like a deduction. So this, what is coming in, if it's a reactant, it will then be deducted by the how much of the reactants getting reacted, and then the product will then be formed or added to it. And this one as well, this is then like a reduction calculation. So this is then minus that one becomes this. So I make sure that this, none of these, all of the mass balance has to be like a positive value. That's the one. And then I click solve, and then it solves. So it solves over here. So we have like 1.52, 1.52, 3.8, 3.8. So if you can see, compare it with the sequential. So this one 1.51, it will then converge in quickly, but then the 3.8 will then take some time for this guy to go to 3.8. So this is then the way I solved this was that using that sequential modular approach. Then the way I solve this is then using that equation oriented approach, right? So you can see, you can have a feeling now that sequential modular will have a slight problem if it's a small problem, or it's a bigger plans, it will have a more bigger problems to solve compared to the equation oriented. Hence um, for the uh, for real life plants, we tend to use flow shifting software that has the capability of doing equation oriented. So things like this, if you know gproms, if you know like Romeo, I think these two ones that I know are having the capability of equation oriented, and also software like Aspen Plus, it has also the equation oriented feature as well. Yeah, and not only the sequential modular, which is its traditional way of calculation, it also has this equation oriented. So it's something for you to explore. Yeah. So that's about that. So you could also do the optimization over here. For example, I don't know. So you could also like maximize this, maximize the amount of C. So then you can see, we can see here, for example, in this unit operation, we have X conversion as the performance evaluation, and then we know for sure that the conversion is a function of temperature. Yeah, if it doesn't have any side reactions, it's only a function of temperature in this case. Also, a functions of this purge, right? Because the more you purge, I mean, the more you purge, the less A going back into the system. Means if lower the A, that means you will have a lower product, right? So you can do something, something like that. Okay. Okay. What do I want to tell more about this? Do you have any question before? Because I thought I had something to tell, then I don't remember. Um, yeah, you could do a lot. Yeah, for example, I don't know. Say for example, in this case, if you have mass balance in the plant, like I mentioned to you, I was involved in like designing 7 chemical plants or something, and everything dozens more, and then most of them we do it in them because it's called chemical plants. It's very difficult for the thermodynamic model to predict what's in it correctly. So we use like a shortcut like this in Excel. So this is then our tool. And then for example, if you have like a purge, right, something that you can control. Say for example, I want to maximize the B, so I want to copy this. No, I cannot copy. If I want to maximize this, I have to redo this again. So what we could do in this case, for example, so now we can do this, yeah. So we have like reflux, purge is then I'll put it here so that we know. So we have purge 20%. We have C is then 15.24, right? So we could also say, well, now if I increase purge, for example, and then I redo this like that, and then you can see, so 30%, it's like a 14.88, and then now it's not really like difficult to predict in this case. If I then increase this to 40%, and then you can see so 40%, 14.55. Okay, 14.55. This was increased, I don't remember. 30%. Are you guys seeing this or not? 14.88. I made a mistake here and nobody comments. So I thought that you guys are all awake or not? Well, anyhow. So you can see the more you purge, like I mentioned to you, the more I purge, that means we are losing more A. That means we are getting less C, right? As this indicates. So in here we can say if we have like a limiting factor on the purge, for example, if we can limit, I mean the lowest purge that we can allow is 20% due to, I don't know, impurities or whatnot, and then the highest purge that we can allow is 40%, and then in this case we are sure that 20% is then the optimum value where we can get the highest yield of C. So that's basically what we could do, and that's what it means over here. Now I remember. Okay. Now we go to the next topic, which is this is more on like a general knowledge, but just ask me if you have any question. Yeah. So what people call like a real-time optimization. So what is this basically? So as I've mentioned to you, the difference between the sequential modular and equation-oriented, and then the many recycles that we have in real life. And then most people who are going to do this real-time optimization, they tend to go for the EO approach. So it is based on the equation-oriented modeling. So you could also read this in the article that I shared with you. So equation-oriented modeling, and then well, the article was written in 2011, so it was like it has this record. I don't know how they get this record. So about hundreds of 300 of RTO using commercial flowsheeting packages, and then it deals with in our case we have only like a mixer and then reactor and then separator and then splitter, and that's it's only a 4, right? Mixer, reactor, separator, and then purge. So four blocks, and then on like a few equations, maybe like dozens of equations if you can see. And then well, in real life they are much more complex, hundreds of thousands of equations with 40 decision variables. These numbers are coming from that article. Yeah. And then depending on the model complexity, and then because as you saw, I have this purge and then I have the separation performance, I have the conversion as my decision variables, right? But in real life, we don't know how much then the conversions, we don't know how much then the separation factor. So these numbers that I put in the Excel, these are part of the parameter fitting. So we fit first the parameters that we will use in the model, and then based on that fitted parameters, using the current data, we will then use them to optimization, like I did already. So I use that model to do the optimization to maximize the C yield. And then typically we have we have a plan. It has like a different levels or hierarchical levels of decision. So it goes from the top down, like this, top down. So we have from the planning. So this planning, it takes like what to make. So what type of goods that we want to buy, and then what type of products that we are going to make. Yeah, given the current economic situation. Okay, so given the current economic situation, which means it defines how much the price of the goods or the raw materials, and how much the price of the energy, how much the price of the products, and then we take that into account. And obviously, these numbers, they are difficult to find. Sometimes we have to assume something, and then this exercise will be done like in weeks time or in once a month or something. And then once we know what type of goods or what type of raw materials, how much to buy, and what type of products, how much products that we are going to make, we will use this information down into the scheduling department. So that scheduling department will then schedule for us, okay, so this crude coming next week, and then we will then use that crude, and then for the whole week to make this and this product, this and this much. And then the following week we will use a different type of crude, or we'll then use we mix crude A with crude B. So they will then make this scheduling on day-to-day basis. Okay, so not day-to-day basis. So they will then say, okay, to this day I will use this code, tomorrow we'll use that code, tomorrow that code. So they will then make it like a scheduling. So this is either 1, and then this is 0, I mean it's another 1, there's another 1, and so on and so forth. So they will use this code 1, and then maybe this is code 2, and maybe this code 3, and then maybe this code 3 as well, and code 1, then this is, for example, for the whole week, for example. Right? So we know that we will then buy code 1, code 2, and then code 3, and then that is then the schedule for the entire week, for example. And then they know which coming in and then which product should go out, should they make, and then it goes to the what they call like a RTO, real-time optimization. So in this RTO, they have a plant model. So they have a plant model like the one I showed you in the Excel. It's just in Excel. They have a plant model in that using that EO type of approach to give a direction on what are the set points that we have to put into the plant, into the operating conditions, right? So how much do I have put? How much do I have to burn as a fuel? How much then the reflux? How much is then the pressure? How much then the temperature, and so on and so forth. So they use from the plant data. So we have the plant data, and they make the model, and then from that model, this RTO model, they will then use this model to say, right, what are the set points required for the plants, and then those numbers will then be sent back to what they call like an MPC, the model predictive control, or for your as a set point. And then LPC will then also try to optimize in a way for the profitability as well, but from the control point perspective, and then that information will then be sent to our DCS. Yeah, so we have like a different time horizons over here. So weekly planning, daily scheduling, hourly optimization. Yeah, it takes hours. For example, simply because typically the RTO, I mean, if we click run, if we click that solve, for optimization, it will take more than a minute in most cases. So maybe also like a half an hour or 40 minutes or 50 minutes or something. Okay, but it will then get the data every hour. So I will then consider uncertainties and information and IT limitation. So we have to make sure that we put in relevant information and then omit irrelevant information, and then there is also a problem on the lack of sharing relevant model information, constraint, and pricing, because these are different departments. Yeah, as you can imagine, this the planning department, schedule department, the optimization engineer, this more process control engineer, this then the operator or process engineers on the field. So these are all different departments. So obviously, as we know, practically speaking, all these informations, if they are like handed down or passed down from people to people, they can change, or they will change for sure. Not they can, but they will change for sure. And then we don't get update as much as possible. Yeah, this one is for machines, so we can get update like in seconds. But then from here to there, and then from here to there, and then from here to there, it will then take some time. They will lack information. There is inconsistent information. So all of these factors put together, these are some of the challenges that we are facing to have this kind of like an optimum organization or plant to run. So I did quickly explain each of the department. That will go very quickly as well here. So like a weeks or months, like I mentioned. So based on the economics and then all the forecast for the demands, forecast for the demands of the product, forecast for the price of the crude oil, raw material cost, and price for the product cost, among other things that they will have to forecast. And then they will then do the optimization using that linear programming that we have seen in the meeting number 2, right, where we touch on the linear programming, where we did the exercise on the refinery planning. So they can then tell which feedstock to purchase, right? Is it crude 1 or crude 2, and then which products to make given the constraints of the plant that we have, because we cannot use crude 1s, we cannot use double of the crude 1, so they are constrained to obey, and they will then tell how much each product to make. And then linear programming, like I mentioned to you, and then this model update is manual, because we will need to have work with the pricing and sales people for the economics and the forecast. We'll need to work with the people on the field for process engineering to get to the to know what is then the yield of each and every crude, and then what are the operating modes, which refinery is down or which unit is down. So all of this needs a strong collaboration and then a regular meeting between departments. So that's the planning, and then this is then basically the goal. Then basically what they need to tell to the next group, which is then the scheduling group. So they do the scheduling to advise the operation on daily basis. So this today what code to make, and then tomorrow today what code to buy, what code to process, and then tomorrow the same thing, and so on and so forth. So the timings is very important, and operating mode changes. And then here the other goal is that they want to avoid storage problem, because in the refinery or in chemical plants we have storage tanks, right? That they are limited. So we want to make sure that they are all like always yeah, I mean there's no idle time, because idle time means we are losing time, and then we are losing money and resources, and then we have to make use of the as much as possible full capacity, and then the full utilization of all units. And then to do this scheduling, because compared to the planning, which is we can this one is much easier, yeah, as you know already in the second day linear programming. You know the yield, you know which crude, you know the yield of each crude to all products, and then you can solve it, yeah, if you know the prices. This one is a bit complicated, because it's more like a yes and no, yes or no answer. It's a combinatorial problem. So what it means is that we have on day one, so for example, day one, day two, day three, day four, day five, and so on and so forth. We'll need to answer whether crude one is then being processed on this day or bought on this day, and then is it like crude one or crude two, for example, and then crude two. So we have like either it is there or it is not there, and then either crude 2 is there or not there at this time. So the more crudes that we are going to process, and then the more time horizon that we are going to evaluate, you can see the combinations will then go sky high. So this one, from the optimization standpoint, this is a bit difficult. I mean, it's very difficult to solve as well, even though we can make it linear simply because of its combinatorial problem. Okay, so this is more like an integer problem to solve. So you will learn, or you have learned about integer optimization in the optimization course. And then we move on to the next level, which is then the RTO and process control. So they mix it together. So we have the RTO, yeah, the optimization, which then gives a set point to the MPC, and then that MPC will then tell the basic process control system on what to regulate. Yeah, so it's an hourly basis, like I mentioned to you. So we have like a continuous feedback from the process, like if it's like hourly, so that means every hour we will then get data from the plant. We'll get data from the plant, yeah, and then those data we have to then clean them, and then we have to make sure that relevant data to the model are obtained, right? So every hour we get the data, we clean the data, and then we get the relevant data information needed for the model, for the RTO model to run only. And then we run that model for parameter optimization, because we need to make sure that all of these parameters, like I put as well in the Excel, I showed you in the Excel, the conversion, separation factor, the split, whatnot. So they have to be calibrated for that specific time frame. And then once they are the parameters are fitted very well, or well, I don't know, depends on your engineering judgment, and then you can then say you can then use that model to optimize for the next 1 hour. Yeah, so that in next 1 hour you can then tell the MPC, okay, so these are your new set point, for example. And then this model is calibrated from the nonlinear, well, it's always nonlinear, calibrated on the steady state model. So if you know that your plan is dynamic, but then that means you have to then be able to find a steady state situation from which you can then calibrate the model. If it's like very dynamic like this, and then then you cannot use this type of data to calibrate your model. Yeah, it has to be like sufficiently steady state, even though they are here and there. Well, you could argue as well this is like a kind of like steady state, right? But I think you get the point. Yeah, I mentioned to you that the success RTO, because it's all like a different disciplines and then different organizations. Yeah, it requires the support of the entire organizations. What are the supports? I will then let you know later on. I think it's quite simple. So RTO is then a steady state model. Yeah, so we have a steady state model over here in the RTO, and then we have the economic numbers on the prices, and then we have the operating limit or design limit, and then we have the data that we get from the plant. So we get the data from the plant over here, yeah, to do our parameter optimization, and then we have done we run the RTO, so we get the results, and then that results, which is then in most cases is about the set points or what to operate or whatnot. It goes to the MPC, and then MPC will then take care of the rest for the controlling part. So it has to make sure that we will then meet the set points of the optimum decision variables defined by the RTO, obtained by the RTO. Yeah, it takes into account this RTO, it takes into account the economics, like I mentioned over here, and then equipment efficiencies is over here like that, or even like here, and because this is also coming from the data fresh from the plant. So it's all about the fouling, catalyst deactivation, and I mean a real-time condition that we get from the plant in such a way that we can then update the model, and then use the updated model to do the optimization. So some notes on the RTO, like I mentioned already. So for parameter tuning, it has to be like in a sufficient steady state condition. So sufficient, yeah, is the key, because you will never be able to find any like a straight line in steady state conditions. It's never going to happen. And then once we how do we know this sufficiently? So this comes from the we have to check on the means. So we have to plot the means for every like this. Right? So it's time. So is the mean value constant or standard, or the variance also constant, and so on and so forth. So we will have to do like a statistical analysis on the data for during this time period. If this is okay, then we'll then use this data to update our model. Yeah, if during this time period it goes like this, then we will not use this data. Yeah. And then all of these logics obviously depends on your the knowledge on the plant itself, the historical data, and also your engineering judgment. The engineering judgment is very important, because many of these data, they're useless, they don't make sense, and so on and so forth, right? So the knowledge on the plant, and then the knowledge on control, the knowledge on the process, the knowledge on thermodynamics, the knowledge on modeling, they all have to be there. If we lack any one of this knowledge, it's not going to happen. If we lack any one of this knowledge, this RTO, forget about that. Forget about this RTO. Forget about that. If you don't have any of this knowledge, and then so when when we can then check it and it's passed, and then the RTO can be run, and then it depends on the time duration to move from the old to the new steady state. And then another note, I mean, this is also I mentioned already. So decision variables on the RTO is a set point, and then upper and lower limits, for example. And then all of these numbers on RTO, you could, for example, in this case, you could make this like online. This way they call it real-time optimization. So not necessarily like online, but it goes also like offline. So you have some guy over here, or maybe a team or something. So they will then evaluate the results of this RTO. If this makes sense, they will then I mean, if it doesn't give, obviously they will have they will have to program like a set of criteria where if the results of RTO is still within this boundary, they will not do anything, or then just let it pass to the MPC. If not, then they will then ring a bell, and then they will have to check whether they can accept the results of RTO, or they can just neglect the results of the RTO. So that's basically why was I there? I don't remember. Anyhow, I don't remember why I was there. So the key requirement for the RTO is that if there is any change here on the operating conditions, because the way we want to run the plan is we just let it run in a stable mode, so we don't want to change anything once it reaches steady state. So if there is anything changed, then we'll then see is the change is going to go to the right directions or to the wrong directions. If it goes to the wrong directions, then what do we do? Okay, if it goes to the right direction, yes, fine, and then we can go get some more coffee. So if there is a change in the operating conditions, feedstock, any other constraints, and also the prices, which is very important as well. So if there is any change in this, like a 4, and then we will then go back to our RTO model to see whether we are heading in the right direction or not. Um, and there's another point of view as well. If our plan runs like this, right? Which then what it says over here. So the variability is minimal. And then if our plan is running like this, and then we know that if we change something, it will also like run like this, which is also like very steady. So it's not necessary to run this RTO and then connect it to the MPC. So we could run this like an offline optimization. So we can just take a model and use that model to do some sensitivity analysis or case studies, and then we'll then say and then we can then and see which directions that we have to take. Yeah, so it's more like a what if sensitivity analysis or case studies kind of work. Last on the notes on RTO. Yeah, I think I've mentioned this indirectly. So the controller envelope varies depending on the complexity. So we may not be able to model the whole plant. Like for example, in our Excel file, so you know that we model the reactor, we model the separator, and then we have model the split factor on the purge. So only these three. But in reality, there are many things, yeah, around the reactor. There are many things around the separator. There are many things around the reflux or whatnot, or the purge or whatnot. But then we don't consider them as very important. So depending on the whether they're important or not, and depending also on the complexity, so we may opt or we may choose whether to include them or not. Yeah. So example, instead of like having the kinetics, we can use like the conversions, as long as we know that the data on the conversions it is stable. Yeah. So depending on the complexity, depending on also the value that we have to put, the effort that we have to put in to get the additional value for that complexity. So we really have to weigh the pros and cons on whether to go for the for doing the RTO or not. Yeah, it says also some protections use RTO to provide coordination function for individual MPCs, because this is for the whole plant or a big chunk of plant, while the MPC is more like an individual process control, right? So it has to coordinate that because this will then, for example, MPC for distillation column, for example, it will then tell, okay, what to control, what to adjust in such a way that I can then maximize the product flow. That's it, right? But then, in a bigger picture, it could also be like, well, that kind of product may not need to be maximized, but we have to do something else in such a way that the profitability for the whole plant can be maximized. Yeah, so one unit can be like can be sacrificed in such a way that the whole team for a greater good, basically for a greater good. So it's from the point of view of the operation. So this is then the primary, and then the secondary, as you saw in this what was it? So here, so if we are here, so our boss is then the MPC. So they will then tell what are the set points, but this boss is then the it could be the RTO. Yeah, if we have the RTO, so they will then tell what are the set points. It will then see whether that set points make sense or not, or whether the multi-inverted variables make sense or not, and then they will then tell the put it into the process control on the field. Yeah. This is the one, the conversions and throughput. This is the the example that I put on the distillation column is basically suited to this part of the example, even though it's about sacrificing one area for the greater good for the whole system. Combining reactors, multiple units, so units with larger cycle, and so on and so forth. So these are the situations where RTO can be useful. Okay, so RTO model detail. So it typically covers cover an entire unit, but not everything has to be modeled in detail. So I've been mentioning this again and again. So a more complicated model is difficult to match the plant data, right? Well, again, your data, number one, we have to make sure that the data is correct, which in most cases the data are not correct, and then we don't have any trust in the data. We have to do like recalibrations of the data. We have to buy a new equipment, new transmitters, and so on and so forth, such a way that we can have a high confidence on the data that we obtain. So once we get the data, if we have a too complicated model, for example, it's going to be harder to maintain, right? So you need to have people who have knowledge of the process, knowledge of the equipment, knowledge of the model, in such a way that he or she can update the model if any update is necessary, can then debug what the problem really is if there is any problem. Okay, and then it's also like difficult to converge, yeah, if it's complicated, and then we have to balance with the value contribution that we will get, yeah, by having this complicated model. I think I've mentioned this as well. So when we model, that model may be representative enough for the actual plant operation, but you may be still wrong from the operational point of view. For example, if you have like a you can model, yeah, if we have like a identical heaters, and typically we can then model like one heater, yeah. But then in real life, these identical heaters, they may perform differently, right? They may perform differently because of the I don't know, different aging, different type of exposure. There are many details on the field that can make identical unit operations behave differently. Right? So we need to be careful. We need to be careful whether we want to model identical unit operations as one unit operation, or we have to let them like a separate unit operations, for which we can then tell, okay, to maximize gasoline, for example, I have to use that kind of unit operation. I mean, unit operations on the right, for example, and then if I want to maximize gasoline or diesel or the other way around, I will have to use the same unit operations, but on the left. So it's that kind of situation. We have to be well aware. Yeah, you have to be well aware. Also note that not all relationships for the RTO model, not all the performance evaluation equations that we need for the RTO comes from the first principles. We could also use like I showed. That's why I showed the Excel file before at the beginning. So we could also use like a straight line correlations for the conversions for the separation factor, like I showed in the Excel files. So we could also do so, yeah, as long as these numbers are backed by the trustworthy data and that it matches with the common engineering sense. Okay. Yeah, I mean, in the end, engineering judgment is really required. And then model update. Selected model parameters are updated based on average plant measurements. We know this already. And then which adjustments do we have to, which measurements that we have to adjust, and which model parameters that we have to fine tune. It requires the experience on the plant, the experience on the process, and then also the engineering judgment. Again, so there is no, it's not really black and white. Not really black and white, like 1 + 1 = 2. But it could be like this 1 + 1 could be like a 2.5 or 1.9 or something. But it cannot be like lower than 1 or larger than 3, for example. Yeah. So it has to be, we have to be really careful. So parameters that change on the slower time scale means that if it's like something like this, so it may not be appropriate to be updated every time. And then in practice, trial and error is we have to do that. And then yeah, to have a better fit of the plant and the model. And then once we update the model in this, and then we then use the model to optimize the profitability of the plant. So we only do the optimization using the most updated model. And then the objective function is always profit, yeah, which is then the product sales, and then minus fixed cost, minus variable cost, energy, and so on and so forth. It includes all of this mass energy balance, thermodynamic kinetics, and so on and so forth. And then this then the mathematics from the article that I picked. You can read this, yeah. I mean, but bottom line is then this number. This is the bottom line. So these 2 points are important in this case. Some challenges on the RTO, like by now you won't have a feeling already the type of work or activities that are required. Yeah, so we have informations to convey from different departments, so we have to have like a strong coordination between departments to get consistent data, and then to avoid conflict. Yeah, we're not here to pinpoint to point the finger to anybody else. We have to work together, get consistent data, talk together, so that we can then have a good direction, okay, for the plans to use. Yeah, we have also difficulties in determining the prices for intermediate streams. So if you want to make this optimization, so we have to know what the prices really are, and then sometimes we don't know what the feed composition really is. Yeah, it's also like a challenge in these numbers, and then also, yeah, because it has in it creates this decision. I mean, the optimum set points. So that numbers, it has to go to the process control. Yeah, because if these numbers over here, it is not conveyed to the field, I mean, it's useless. It has to be put in the process control layer, or in this case the MPC, so that MPC will then can tell the set points for the process control system on the that BPCS stuff. Okay, because they are working in the like that BPCS is very detailed. This one is slightly less detailed. This one is there also not so much. I mean, slightly also less detailed than the MPC, and then up to scheduling and then planning. So if we go to here, so if we have a model, so you can see the fidelity of the model. If we have a model for this, model for that, model for this, model for that, model for this, so we have all of these models. This model is the one that has the highest fidelity, the more details and most accurate. And then this one is then slightly less detailed, slightly less detailed, slightly less detailed, slightly less detailed. So in this case, this guy will never know what is then the how much is then pressure temperature. It doesn't really care on pressure temperature. Yeah, it cares about the crudes, and then it cares about the products. It cares about the energy cost. And this is more on they get this crude products information, and then they care about their tankage. They care about when to use when to produce what, and then when to use which crudes, and so on and so forth. And then this is more on the, yeah, what are the operating variables that are important, and then the plan constraints that are important, in such a way that if I obey these constraints, I can then show the directions for the for a better solution. So it doesn't take into account all of these valves, all of these recycle lines or not. Yeah, it doesn't take into account all of them, and some just only important stuff. And this one is it could look into a little bit more details, but this like a model of the field, it can be very much sophisticated. Yeah, I think I mentioned that the RTO may need to have, because we need to adjust the parameter. Yeah, some parameters need to be adjusted often, because some parameters may be more important, and then if it's not there, so we cannot really show the results of this RTO. So so we need to make sure that specific parameters, they have like a regular update, and then that particular instrument, it needs to be maintained and then replaced, and then or repair if there's any need to do so. Yeah, so we'll have to have some investments over there. And then you know that it requires a higher level of expertise and commitment. I mentioned these two already over and over again. And then within the organization itself, that organization should have a strong central engineering group. Yeah, so I get this from that article, which I also agree. So if you don't have any strong engineering group, and then one people will not be able to understand the work of the other people, and then they don't have like I mean, if they're not good engineers, forget about this RTO. So we need to have a good engineering group who understands how to model the plant, how to control the plant, how to do optimization, and then to have I mean, they typically have like a good chemical engineering judgment. So if you have these people, and then they are grouped together to maintain these RTO models, and then they are like a clear technical career path for these very specific individuals, yes, you can apply this RTO in your organizations. But if you don't have one aspect of these factors that I mentioned, you can simply forget about the RTO. Yeah, don't even dream or talk about that. Yeah, because it's very specialized personnel, and then typically what we see is that the so-called well-rounded engineers who knows only like the surface, and then they don't know what happens or what to do if there is a problem on the field, because as we know, the devils are in the details. So we have to jump into detail to solve the problem. This one is the situation that where we can use RTO. Situation where we can use RTO. So if we have like a profit graph like this, and then goes up and down, but it's quite reducible, then you can use the RTO. We can model this and then use the RTO to give some direction. But if you have something like this, yeah, it's very dynamic, too many disturbances, which we don't know. Is this really a two disturbance coming from the very crazy plants, or we have like a strange data out of nowhere or whatnot? There are some lags. This is the things that we don't know, and we cannot. Then it's very difficult or too much effort to debug this plant, debug the plant. So we are advised to avoid using RTO for this situation, and also if it's very consistent, yeah, there's no need for the online optimization. So because it's all consistent data, so we can just simply make an offline model like what we have been doing, and then use that model to do some sensitivity analysis or case studies, and then we can then get that data, the optimum set points or whatnot, and then put it into the control systems like manually. Yeah, there's no need for that to be like an online. Up until here, do you have any questions? No? So if there's no questions, then it's very good. We can finish early. So the last chapter, the last part of this topic is about. So we have talked about the how simulators, how the calculations behind the typical simulator software, and then which type of calculations are. Yeah.
Sorry, actually I have a question. I just my mind doesn't work just now. Okay. I have two questions actually. First question: the Excel file that you show, do you mind if you share with us, or it's not possible?
Yeah. Well, I can share. Yeah. I mean, yeah, fine.
Okay.
Next question.
Next question. Okay. Another question: this RTO, right? This data optimization. Is it a common practice in industry, or only or mostly in the oil and gas or refinery industry only?
It is common practice in companies or organizations that have this.
So meaning it's not like a compulsory thing. It's like also like optional. If they have this, then they can do, or they must have this.
Yeah. So some companies, they think they can do this, and then they ask another company or third party to make like an RTO model or whatnot, and then one is being deployed. There is no like I mean, the owner is that, I mean, that company, say for example company A, they hire, they think they can do RTO, or they have some sufficient servers, or they need to do the RTO somehow, and then they can they hire company B to make some RTO models, because because company A says, well, we don't have people to develop it. So that's the first I mean, that's the first how to call it? That is then the first item that will fail this RTO project, because when that model made by the company B implemented, only the people in the company B have the knowledge to make the model, and also to update the model, and then to maintain the model, right? The company A who wants to have that RTO, they don't have that kind of capabilities. Hence, when that model is with their hands, they don't know what to do. So it's just a matter of like a publication. So we have this RTO, blah 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 blah. But then, do you use that? And they say, we don't really use it. These RTO models made by the company B is just like a bullshit models. So we cannot use it. The model itself is not really accurate. So we cannot use it. So that's their excuse. Because none of these models are accurate. Yeah, you know, I mean, if you work on the fields, you know these data. Even we have questionable data. If we try to make accurate models, that means that model is obviously wrong if it's accurate. because you can fit all kinds of data. Yeah, we can fit all kinds of data, but are these models fit to the data? Are they make sense from the engineering point of view? Are they make sense from the mass energy balance? Are they make sense from the thermodynamic point of view? So these are the things that we have to be able to evaluate in such a way that we can say, yes, this RTO model is good enough to give us direction. Yeah. So without having that capability, it will not happen. So only companies who have that certain capabilities, that has like a very good engineering group, it has knowledge on this, it has people who can model, it has people who can simulate, it has people who can optimize. It has this kind of people, and then there are like a clear technical career path within that organization. Yeah, if he has that people, that means they can make it. If they have like a clear technical path, that means these people who can make it, who can build it, who can maintain it, they will then stay within that organization because they know they have a clear career path that they can go to, right? So if they don't have a clear career path, yeah, on the other side, they will not be able to, they will not find this type of work interesting because you will need a lot of focus, you will need a lot of technical details on this. And then if there is not clear what is then my next career path within the organizations, they can just simply leave for better, I don't know, career satisfaction or better job somewhere else. So these two things is the what I see is then one, and then two, and then one is then related to this expertise, yeah, and then three, the commitment is then the necessary things that an organization should have for them to implement the RTO. If one of these three items are not there, well, they can try, but it will not be successful. That one I can guarantee.
So I mean that if a company decided to do RTO, then they cannot hire external. They have to have like an internal department that do these things, like the whole day focusing on this.
Yeah, exactly.
So knowing about these challenges, I suppose very few companies or organizations are doing this.
Say it again, I think.
Yeah, I mean, knowing about these challenges, I could imagine that not so many companies that committed to this.
Right, exactly. Yeah, not everybody can do this. Not every company can do this as well. It's very few. I mean, if we see in our chemical engineering community and then in our students as well, universities, if you see people who can analyze data, people who can model, people who can simulate, people who can optimize, people who can do process control, how many of them? How many? Not you can count them by your fingers, right?
Yes.
Exactly. So that's also what is happening in reality here. So and then the companies who can do this as well, you can count them with your fingers as well. So
but does this I would say technology or knowledge, is it like new, like 10 years or 20 years new, or actually already full?
I think this kind of stuff come into existence with the process the coming of the process simulation software. Right, so because this process simulation software comes into the picture, and then we realize that we can model this, right? So and then we have like it's also like requiring like good data connections or whatnot. So I think for the last 20 years, right? I mean the early 2000s or late 1990s, we have this Aspen Tech and stuff. We have Viva. We have all of these kinds of companies. So they're selling software, and then companies who can build this model, they will then use this software to build their own RTOs. And then I think we know that our legacy, the UMIS material for this course, it was in 2002. And then they mentioned that in that 2002 slides that we understand, they mentioned that at that point in time, this RTO was still in its infancy, because 2002 it's not so, it's not as advanced as now, right? 20 years later.
Yes.
This one was still in its infancy, still in R&D. And also another topic that we will cover next 2 weeks. The last topic about supply chain and stuff is also like another still in its infancy at the time in 2002 slides.
But now we can say this RTO is already mature.
It's mature. I mean it's I mean we can, I don't know what mature or not, yeah. I mean we can use it. It's there. Even in here, I think in this article 2000, so in the article of 2011, I think this article is this article.
I mean, if it's already applied in industry, I mean,
yeah,
I could say it's mature. Yeah,
right, so
it's not like in the research.
No.
Still in the research. Yeah,
So,
okay.
it says here in 2000, this current practice of 2011, there are already like how many? See, these hundreds of RTO implementations. So 10 years after that, I expect there will be a lot more, right? Because yeah, more and more companies have this are aware of this, because the benefit is a lot. Yeah, if we can make good RTO and we can then communicate the results of this RTO to the people in the field, the benefit is a lot, because it talks about millions of well, not millions really. I mean, some quite significant, but I don't know about the numbers.
I think if a company wanted to go to this RTO, I could imagine maybe they have to put investment, right? Because it's a long
yeah.
distance.
Indeed. So they have to invest in their own organization. That's the first and foremost. And then
because
once
not just an equipment, right? Because people also.
Oh yeah.
The technology,
engineers. Indeed. True.
Okay.
So,
last question.
Yes.
You mentioned about the hierarchy, right? The most important and most complicated is the DCS, which is the control system. So this one is
very detailed, yeah. Not complicated also, but it's very detailed a bit.
Yeah, very detailed. Yeah, but this one DCS is normally set by computer. I mean, they like every second they check and do the calculation, right? And then you will always moving into the set point, because for example we have a set point, then we always try to control so that the operation is in the set point, right? But then for the MPC and RTO, is it that similar kind of system that they can decide itself according to our constraints, something like that? Like DCS, we put like a set point, so it always go to the set point, right? But for MPC and RTO, do they work like that, or do you have put some constraint, or like set point that it has to follow, or no?
Yeah, what I understand, yeah, this RTO is more in steady state, and then this guy is in dynamic mode, yeah, this dynamic.
Yes.
This is steady state, and then this guy is in dynamic as well. There are some unit operations because this yes, it can be like there's a very, I mean, it's just like reporting data, right? It's just reporting data. Okay. So it will then try. I mean, for example, take the PNID control system. So we have the proportional integral, so we just fix it over there, and then we'll then try hopefully to reach that steady state in its own time frame. And then there are many things that we cannot model. To make that response faster, we need to be able to improve the control system itself. And then one of the things that people do is then they model a certain part of the unit operations, or they make like a prediction, for example, in such a way that they can then how to say it, so they for things that they cannot model precisely. In one example, for things that they cannot model precisely, and they will then use simple like I don't know, like a linear system connecting the x and the y, the input and then the output, and then use that as part of the dynamic process model, and then we use that in our what we call this MPC, or model qualitative control systems. But this is only, for example, if we have like a distillation column in here. So that distillation column, we may or may not be able to model them like using our like mass energy balance and then the flash calculations type of model, because it's very complicated. So in that case, instead of using this like a McCabe type of approach, or mass and energy balance calculations, they just simply use like a linear or a multilinear relationship between input and output, and then use that model to do some optimization.
So meaning that for example, we can say DCS can make its own judgment or decision to how to like open the valve or closing the valve based on the set point, right?
Yeah,
they can like kind of make decision.
Yeah,
right?
yeah.
But is it the same for MPC? Do they also make decision, or we have to change ourselves?
The results from the MPC has to be put as a set point in the control system. I will show you. Very good. I will show you. How do I show you? I will show you a simplified version of a reality, which is this guy. So I have a model. Stop.
I cannot see the screen.
1 minute, 1 minute. Can you see my screen, right?
Only the slide.
So I have a model. This is not a refinery model because I don't have a refinery model for this case. So I have the symmetry model, and in this case we can see, how do I make it smaller? Okay, make it small. So we can see this. This is like a DME plant. DME plant is dimethyl ether plant. What it does is that we dehydrate methanol. So we take water from methanol, where we produce DME and obviously water. So we have a methanol coming here. We have a methanol. I'll show you this. I'll show it. So we have methanol coming here. It goes to the tank as a makeup, right? It goes to control level, and then we pump it. So we pump the methanol from the tank, and then we send it to like a series of heat exchanger and to the reactor. And then in this reactor, to simplify this, I think I modeled this like a conversion reactor. So we produce like we react 80% of methanol in here, and then it will then be exchanging heat to the feed, and then we reduce the pressure, and then goes to this distillation column. So these are the trays on top of the feed stage, and then these are the trays below the feed stages. And then it goes to the condenser, to the flash drum, where we have the gases out if there is any, and then we have the reflux over here, and then we have the DME obtained from this stream. So this is the distillate stream of this DME column, and then this is the reboiler, and then we have, obviously we separate DME. So it means we are left with water and methanol over here. It goes to the second column. So the same setup. So we have methanol goes to the top, and the distillate it goes back to the tank. Yeah, and then the wastewater goes down here. So it goes to waste. So this is the dynamic model. We have with all of this process control, so we can see this example. Yeah, we have I have also like a main control. So I have like a level control for the tank. I have like a flow rate control for the methanol. How much methanol do I want to send to the reactor? And then there's some basic controls on the distillation column. So we have like a level control on the reflux, and then pressure control on the what do you call this? The gaseous stream, if any, and then we have a reflux flow rate control, and then the temperature control on the reboiler. So the same setup is applied in the water column. So this is the dynamic. I will show you. This is then this is the same setup in the steady state. So assuming that this dynamic is our dynamic plant. Yeah, this dynamic plant is our real life plant. So these are real life plants, and then we have this data. So I will run this again. I will run this in dynamic. I have the strip chart. So where I put this strip chart, so what I record is basically it's very slow, yeah. What I record is, yeah.
When you say dynamics, meaning that you're changing the operation point at different time, is it?
No, this is dynamic simulation. So dynamic simulation means it will then change. It's dynamic model. How do I say this? So in time they will change. So if I plot this, yeah, I calculate the profit, I calculate the dynamic the flow rate of the product, and then flow rate of the input, and then the variability, and then I plot them. So it looks something like this. So if you have time based, like today or tomorrow or next day, so it's time based, and then you can see how the plants behave. So this is not really stable plant, as you can see over here. So it's really like up and down. It's not really it's not really stable. So from the lecture that we have had already, so we know that the RTO will not be able to help on this situation. Yeah. So I don't know what happened. So I will have to dig deeper on the how to make this plant stable. But nonetheless, it is not stable. You can see this graph going up and down. And the green one is the profit calculation. The DME flow, the product is on the brown line, and then DME sales and the blue line, and then the raw material cost in the red line, and the energy cost is somewhere here, which is relatively cheap compared to the material, and then yeah, compared to the material costs.
But do you have like a manipulative variable or something, or you take from the actual plan data?
We have the manipulative variable, like I mentioned to you.
Which one is a manipulative variable?
The plenty. Say for example this one. This is the I can zoom in here.
Meaning at the same time you have all many points where you vary the parameter you set yourself.
I don't understand the question, but I will show you.
Okay.
Because I don't know if you understand what the difference between the. Do you have any idea what the difference? Because before we go into further, what is the difference between steady state and dynamic model?
Steady state meaning that it does not change upon time. It's the like equilibrium, we say.
Yeah, and then dynamic.
Yeah, so and dynamic it changes upon time.
Yeah.
But the changes, there must be like an input value that we get, and then we expected an output value that, for example, profit is the output that we want, right?
Yeah.
The input is where we change the value. So at which point that we change the value, which one we manipulate it? Is it like opening the valve, or the flow rate, or the temperature, or the pressure, or basically we change all at the same time?
You change all at the same time because this is a real life plant. Wow, this is a real life plant.
So this
open quote.
This meaning this the flow that is changes across time, and you define it based on the actual. I mean, yeah, the actual plant.
Can you see this? Can you see this? So I have this is then the flow rate of methanol gets into the reactor. This is the flow of methanol over here. So my set point is 8370 kilogram per hour.
Okay.
And then the actual flow is somewhere around here. So you can see they're changing.
What makes it change? Do you say it changes or?
No, I want to have it fixed.
Oh.
I want to have it fixed. See, that's why we have set point. We want to fix it to the set point, but then your process variable, it is somehow changing because there are many interconnecting situations over here. So in this case, we have because we have so we have a recycle of the methanol. So it can also like go. I mean, it can create disturbance in this tank, right? It can go up and down depending on how much methanol that you recycle, and then this going up and down is tried to be, I mean, this controller try to dampen that going up and down of this level by adding more of fresh methanol in here. But then you have already some disturbances, and then this whole thing, this whole distillation column is so many stages. I think 20 stages in total. I don't remember. And then we have like a control on the distillates. We have a see this then the reflux flow rate. So I want to have it like 17,926, but it's somewhere here. So it's not really how do you call it? not really constants. Well, you could say, well, I can also change the controller parameter. In this case, the KC and then the time integral. You could do so, but this is just like a basic to share. Yeah, you could try to stabilize this plant, but currently this is then the current situation that we have, which is very unstable, but nonetheless it is there. Yeah, again.
How is the initial condition? Do you use the Excel to choose your initial condition?
Initial
at time zero. At time zero.
Oh, this one you have to start from if you're asking how to model this, you have to start from the very beginning. So you have a tank, and then you try to pump it, and then you add all of this equipment, and then it will then run. It will then run in dynamic. So the same thing like in the plant. So you have a tank, right? It fills of liquid, and then you try to pump it and then recycle it, and then until you have sufficient pressure, and then you will then open this valve and then let it run through the exchanges, and then this guy will then make sure.
It was exactly like an actual plant.
Yeah.
Can you mean that at time zero recycle flow is zero?
At time zero recycle flow is zero. Yeah, you could do so.
Oh, okay.
Yeah, if you close this valve and then it becomes zero.
Okay. Yeah, this is like an actual. I think interesting. I want to know more. But I think you continue. Yes.
So what I wanted to show, for example, this is an our plant, and then we have like I showed you the one independent variable, the feed flow rate to the reactor, and then another independent variable like this one, reflux to the column to maintain the purity of the or to control the purity of the DME. In this case, the DME purity is at 1, and then the flow rate is then changing from the 1000 something. See, you can see the flow changes, and then the all of this information. Well, not all. Some of these important informations, I take like a reboiler for this column, and then a reboiler for the other column, and then where was it? Where was that? I plot it. Nah, it's going to hang. Anyhow, no, not hang. So I plot it, which I lost that plot. Anyhow, let's stop it again. So then I can see. So you can see how the profit. I mean, all of this. This plan is somehow not really stable, and then they can see the whole calculation is not really also. I mean, it's not really stable. So it's not a good situation to do like an RTO optimization for this type of situation as we know it. Yeah, because we don't know whether the changes that we make is going to put us into positive or negative directions. But nonetheless, suppose that this is like a stable situation. So what we do is that from this real plan, we try to model that. Yeah. So this is then assuming this is then the model that we have from that real plan. So which is then a steady state model. So we have so I have the same tank, and then the same series of heat exchanger, reactor, and then column, and then the kind of column. So I have in this case. So in each of these, you have your independent variables and then dependent variables, and then to make it simpler, I take only, like, for example, in this case, I take the ME flow rate, which is this stream, and then the concentration, which is in the 99.5, and then the reflux flow rate, which is the 4000. So the reflux flow rate is then here 4000 or photon, and I take the duties of this column and that column. And then if I put like $700 per ton for the DME price, I can then sell 4,500 dollars per hour. And then the summations of these three boilers, I can calculate if I put like a 10 cents of dollar per kilowatt hour. So I can calculate the energy about 200 something. And then in this case, I have like 10,000 of methanol coming in. So 10 tons of methanol coming in. If the price of methanol is 400, I can calculate the profit of 264. So using this data, the static data, the profit is then 264. So then the question is then, okay, now assuming that this model fits to the plan, yeah, this model fits to the plan. So this model fits to the plan. Then I can use the features that the software has, like an optimizer. So I can then maximize the profit because I want to maximize the profit. So in this case, what are the variables or the independent variables that I would want to use? So as an example, to make it simple and quick, I'm using, so I want to maximize the profit over here. So I maximize this. So this is my current value. And then what do I manipulate? So what I manipulate is, only to simplify this, is only the reflux flow rate over here. So I want to manipulate the reflux rate because if I put more reflux, I will end up with having purer DME, but it will then cost me the duty, right? And then I don't get any extra money for selling like a pure DME. The price is fixed 700. So I only use the reflux ratio, or in this case reflux ratio, to as my independent variables. And obviously we cannot go down. We have like a limit, right? In this case, I just put like a dummy 99.2 is then my lower limit for the DME concentration, and then 99.6 is then the upper limit for my DME concentrations. And obviously we know that all of this is then these are strongly correlated with the reboiler duty. So if we then run this, and then for example, yeah, I run this already with I can use this I use this Neldermit, and then you can see this, then I ran this already, so it's done solving. So you can see it was in the beginning 264, so 264.7. This is then my objective function, and then this is then the manipulated variable, which is then the reflux, and then this is then the cost. This is the same gain as this. And then in the first iteration is these are the results, and then the second iteration it will then try to reduce the reflux, and then you will get more money. Yeah, it could be because you will then you may sell more, or or use a lower energy consumption, right? So and so on and so forth until it goes down. I mean the reflux goes down and down and down until the iteration 24 where it says, well, there's no more changes after this, and then you are constant for the last few numbers. So it says that the optimum reflux ratio is about 99.2%, and then the objective function is then $271 per ton. That is then the maximum profit that we get when we change the reflux ratio. Yeah, so we can say, well, now I have this number, and then I could also say set optimizer as specification, so I can use this number and then get the actual number to the optimum number. So if I do this, it will then try to resolve this again. So now I put 99.2, so I put 99.2 over here, and then the profit 272. Now 272, which is 272. So it's not really like similar to the previous one, but it's about the same. Yeah. So the profit is then the 272. So this one is predicted from the like an offline model, right? So we have the model, we have the dynamic plan, we have this steady state model, and then in this case we simply choose one independent variable and use that to try to maximize the the profit. And then in this case, we can see, because it's reflux ratio, yeah, and then I want to see what is then the corresponding reflux flow rate, and it says the reflux flow rate is about 4,000. So I can use this 4,000, say 4,060. So now I can go 4,060. I can go to the real plant, because why can I go to the real plant? Because I can see, I mean, from chemical engineering point of view, we know already the purity is strongly related to the reboilerity, and then reducing the reflux ratio will then also reduce the purity. It will reduce the reflux. It will reduce the reboilerity, and it will then save us some money. So the results of this optimization is consistent with our knowledge of chemical engineering. Hence, it is accepted as a solution. So now we get the solutions. We go to the plant. So this is then the plant, and then I say, so let's run this plant. Let's run this plant. Put it over here. So let's run this plant, and then so the plant is running with the crazy haywire, and then I go to the set point that I to the independent variable that I think is optimal, and then it says the reflux ratio was 4,060, right? So then I can go to this reflux flow rate, set point. You can see 7,000, which is a lot. I don't know why. So so I can say, well, let's see. Let's do the faceplate. Can I see the faceplate? Graph. Oh, I cannot do the graph. Anyhow. So I change this. Yeah, it's very slow. And my computer is not strong enough. So 4,060, which is a huge step, yeah. So this one is, I mean, practically not encouraged, but since this nothing is going to explode here, so we can then this is to demonstrate to you the steps to do this. Not necessary that you have to do this. Just to so now I reduce it to 4,000, and then the valve is then closing. Valve is closing. Yeah, to 6%. It was to 4% in such a way that it will then try to reduce the reflux flow rate. You can see. Yeah, we need to have a strong computer for this. So that's another prerequisite. Okay. So you can see the change. Put it here so that we can see how far. So it's getting close to the set point. So we seem to be yeah, so far so good. And if we look at the profit, well, it gives like I don't know if it is then like a because we have been going up and down, and then seeing this going up is not really converting, or it's not really ensuring that are we really moving in the right directions in a constant manner. Yeah, I mean, because we have been seeing it's going up and down, it's not really stable. So we're not really sure. We're not really sure, even though that our common sense says so. But well, who knows? I don't know what happens here in this imaginary plant. But nonetheless, the reflux is already on the. It's already there. Just like going up and down, but it goes around this number, so it's good. So we are hoping that the profit will then go up as well. So in steady state situation, the profit was about 271 dollar per hour. And in this case, the profit is 2000 somewhere somehow, simply because we have fluctuations of the flow rate every hour. Not every hour. This is every seconds. It's every seconds.
So can you say this is MPC or RTO?
This is your plant. This is the RTO model on the steady state part. The steady state part is then your RTO model, and then you get the results, right? You get the results, which is then the optimum reflux flow rate, and you use that. You go to the plant, and then you bypass that MPC. You put it into this BPCS.
Okay, so now it's already DCS level.
Yeah. Because we don't have any. I mean, in this case, because this is a model already, so it's not really a plant. Yes. So this model is MPC as plant or plant as MPC. It doesn't really matter. That's this one, because we don't have the. There's no model here. I mean, you should see this as a real plant. Good. And I don't know. It's not really updating, yeah, because it's very slow. Slow because of my computer is old.
Yeah, we have run the simulation for 98 seconds and it's still not reaching any steady states or like equilibrium, or you actually changing all the time?
No, this is not changing. We just changed. We just made the change. So for the previous 90,000 seconds, they are still going up and down. So 90,000 seconds is only like, I don't know, a few hours, right?
Yes.
Like 30 hours, so less than 2 days.
Oh, meaning that even from one day, also you cannot get like almost stable values or at least small fluctuations only, but this one is big fluctuation, I would say.
Yeah. But we have to see. I mean, we have to run this for a couple of. I mean, for quite a longer time to see it's stable, and then when it is stable, and then we can then do the what we just did.
Long time is like a week or days?
Depends on the model complexity. And also depends on the plant complexity. Plant complexity, model complexity, they are like intertwined, so they are like a proportional. So the more complicated the plant, the more complicated the model as well, typically. But in this case, a very simple plant, and then the model is also very simple. You can see, but I don't know why the performance is very noisy. That one I don't know. Because this is my old file, and then previously I think I've run this a lot longer than this one, but I never plot the profit. So this whole profit calculations is made for this class only. So I never saw whether they are how stable they are, because what I saw is simply like this, about 7,000. So it looks stable for me. But then if I put like the profit calculation, somehow it looks very strange. But we could see the raw material cost is steadying. Yeah, I mean the methanol itself, that makeup methanol, it's going. I mean, gets to a steady. It's getting steady. That's the methanol.
When you put profit, right? Does it reach? Does it understand that you want to have a max profit or no?
This one, no. This is a plant.
Oh, okay.
This plant doesn't understand. So what it does is just simply, if we put like a new set point, we just put this new set point like what we just did over here, and then we will we have the data. So we have the data on the flow rate, right? So we have the data on the flow rate. We take the data, we record the data. Like this one. So we have the data on the flow rate, we record the data, we have the data on the reboiler duty, we record the data, we have the data on the methanol flow rate, we record the data, and then we multiply each of these data with their corresponding costs, and then we can calculate the profits. So this is then the profit calculation, which is not very stable.
But can we make
Somehow.
optimization like in the Excel, right, where we say that okay, find the max profit where you change at this point. So for example, can you do in this model or no?
Yeah, you can make an Excel model. That is then exactly
in this plan in this model, in this plan model, can we set an constraint saying that okay, max profit, and then ask it to change at one certain point.
No, we don't do dynamic optimization. There's no such a thing. I mean, we have to get one snapshot of time and optimize it using that particular data. So that's why this RTO I mentioned, it's a steady state model.
I see. Okay, understood. Okay, cannot do in dynamic.
No. Because dynamic, I mean, which part of the timeline? Is it now, or is it tomorrow? Is it 1 second later? So each of these seconds, they have different readings.
Okay.
In this case, it's still circling, right? So you can see that the DME is not fulfilling because we are reducing the reflux. So the DME cannot be solved. So it's a 0.5% already. So we will have to wait. So all of this, it goes to the slope tank. So not really nice. So we'll run this and then I don't know, maybe leave it overnight and then save the result somewhere, so that we can. I mean, I'm also want to see, can we reach this to 271 something? Because this is now still a very strange number.
Yeah, the profit seems to increase. No?
Yeah, it's a very strange number. But anyhow, and the this purity is also is not met. So we want to have like it's supposed to be like 99.2, right? So if we see something like this, so we need to really make sure if this model that we have is the same as the. I mean, if, can we model this dynamic plans? Basically, yeah, can we model this correctly? If we can model, and we can use that model to do the optimization like what we just did. So if we cannot, then we have to make sure that we have the correct information. So I think I'm okay with the. I guess I'm okay with the number of stages and then the efficiency of each of the tray. It's just that I don't. I mean, because this tray it has like the standard tray model, and it has different sizes. So I will then do the more. How many stages? Yeah, how many detail.
And this is from the actual running plan or by just design?
This is yeah, this is coming from a plant. So this is 11 stages for the rectifying, and then in this case I am rectifying 11 stages. Let's see, this model. Come on. Okay, so you can see. Oh yeah, I can see. See, you can see. So I have now. Oh, I have 11 stages as well. So we have 2 from here because 1 is then the condenser. So from 2 until 12, it's 11 stages as well from the rectifier. So I guess it's in terms of number of stages, it's the same. It's just that the performance, because this is like in the steady state calculation, we have like an equilibrium based calculation, while in the dynamic, it is not equilibrium based. It's more detailed because we have included the number of the size of the trays and spacings and whatnot. So it will then influence the performance of the column. So it will not be the same 100%. So that's one. I think the rest are simple items, and this is also the same 80% conversion. So it should be okay. So the only source of error is the columns, these 2 columns. So yeah, we'll see. Let's see. I'm not really sure. So what you could do, yeah, I mean, if you cannot model this, like what we just did in the hydro cracking example. So we have this dynamic situation, and then if you have a plant, and then you have a plant, and then you can get the data, and then read from that data, and then we can then do like the one that we did in the hydro cracking example. So we have input stream composition, and then we have, for example, in this distillation column. So we have input streams, the data on the flow rate, and then pressure and composition, and we have the output flow rate and compositions, right? In this case, the distillate, and then the bottom streams, and then we have independent variables. We have the reflux, and we have the pressure, and we have the bottom temperature. So these two three temperature, bottom, reflux, and then the pressure of the column becomes your independent variables, and then you can model the performance of this column. You can model the yield of distillate, you can model the flow rate of the DME. You can model the purity of the DME using these three independent variables in such a way that you can then try to see, well, these are the area that I think I'm confident in, and then you can use that specific area to do in Excel to do the optimization, the one that we did in the hydro cracking unit. So okay, so we are not done yet. So we are here. We're not done yet. But if you have any question, just let me know. Yeah, we're not done yet. But just like the next step, the next part is only we go to the refinery while optimization. So we have this refinery and stuff. So in our example, I have only like this DME plant. This is an example on the one of the article. So Sanko refinery. So I think it's good that you read this article. So they built, control and optimization, and then so make sure model consistency, and then they will integrate this. So I don't know how they integrate this, or is it like a manual communication, or it's like an online platform that they have where each of these disciplines they can take data from the same source. That one I don't know. So there's the different scopes, and then they have this iklan. The results. You can do it later, and then that's it. So then you can watch this later, and then these are the. I think this is the because the next step is only like showing you that DME plant. I think this is the this one, integration of real-time optimization something. So this is the article. So if you go read that, and then it will then give you some you will have some more feelings on what they do. So we have, okay, so it's very rare that we finish this before like on time. Do you have any question?